So if you have a wave on a string, it turns out that the speed of the wave is equal to the tension divided by the linear mass density. Your book shows it to you, but I'm not going to go into it. You can derive it from the fact that from looking at the tension in the rope along its length and looking at the ratio of that from two different points. But basically, we can see that the tension, the speed is equal to the tension over the linear mass density. T equals tension square root of that, right? And mu equals that's equal to the mass of the rope divided by its length, or the mass per unit length. So a rope might have 10 grams per meter or something like that, depending on what kind of string or rope it is. And so if you know the tension and the linear mass density, you can determine the speed of the rope, the wave on the rope. And notice that you can increase the speed of the wave by increasing the tension. This is what a guitar does, right? If you turn the knobs on a guitar, you can change the speed of the wave. Similarly, if you use a thicker rope, you reduce the speed. And so, for example, where's my slinky? You can kind of think of this as a wave. If I do this, you can see the wave traveling back and forth on there, right? And now if I make it much more tense, if I do it like this, so I've increased the tension and reduced the linear mass density. I've made this number bigger and this number smaller, right? And so my V should get bigger, and you can kind of see if maybe you can't even see it all. So you can kind of see that goes faster than, say, this one does, right? You should be able to see that. Okay, it's also true on a rope.